as for us in the US. It's about 9 miles. So if you walk around the drill field in one loop, do you know approximately how many miles that is? Drill field, anyone done that?
It's like a quarter.
No, the entire drill field.
1 mile.
It's a little less than 1 mile. So stretch it, 9 miles, multiply by 9 times. All right? So it's probably from somewhere in Blacksburg to somewhere in Christiansburg. It's pretty long distance. I mean, 18 centimeter, it's about 7 inches. A real tactical pipe about this size. You see it in photos in Alaska and so forth. So I want to pump gasoline at a little less than 10 meters per second over 9 miles. And I want to know how much pressure drop in kilopascal or atmosphere. And how big a pump I need so that I can go buy it from Ingersoll Rand or any other company that I can install with all the plumbing, and I can get this crude oil from Alaska all the way to a processing plant. You want to make a guess as to what that answer is? So when we are done with today's lecture, you have all the tools to actually use Moody diagram to do this problem with the use of energy equation. So that is next lecture. But to set the stage and get you motivated, anyone will make a wild guess? How many atmosphere in pressure drop this is equation to? Give me an order of magnitude.
8.
8. Keep going.
100.
Nope. Keep going.
200.
Keep going.
600,000 atmospheres.
400. I need to overcome a pressure drop of 400 psi to pump this gasoline from one point to another point 9 miles downstream.
Wait, 400 psi or
400 atmosphere, sorry. 400 atmosphere. How big a pump it takes to do that? Big. How big? That engine hanging on the hallway, if you convert that to a power generation instead of propulsion, it's about 10 kilowatt. Oh, I'm sorry, I missed an order of magnitude. No, not kilo. Not kilo. Megawatts. That engine is 10 megawatts. What's the point? It's not a very glamorous industry, petroleum, oil, but it's money. That's why they can afford to pay you so much. You're burning this amount of energy 24/7. This is for one pump, for 9 miles. And from Alaska to Seattle is not 9 miles. Get the picture? Okay. All right, so I hope you get motivated to learn the next practical application of Moody diagram. So you've seen, at least for some of you, no, I think it's most of you, from 21, 24, you've seen what the shape of the Moody diagram look like. Let me again start with the answer and then give you the background as to how we go to that point. So Moody diagram, as told to you in 21, 24, consists of Reynolds number and so-called friction factor on the y-axis. And it's a log scale. You all have you seen this? Have you used the Moody diagram in some homework in 21, 24? Good, okay, I want to make sure. So log scale meaning all to the exponent and the friction factor is given in the y-axis. So the general shape, the left side you already have homework that deal with that in dimensional analysis in chapter 7. So we have talked about this naming of the turbulent transition at approximately what Reynolds number? 2300, and that's academic. Anything from 1,000 to 4,000 is acceptable. So this is not a on-off type transition from laminar turbulent, it's a gray area. And this is the homework solution that we posted. Some of you didn't get it right. You were asked to plot a CP, pressure coefficient, versus that Reynolds number for the homework problem in chapter 7. Do you remember? We asked you for the curve fitting of the couple of data points. Yes? Sure, thank you for asking. Please, those in the back, I can use you to remind me to move it up. The curve here is a straight line. And that's actually is an in-class problem, which I will talk about momentarily. That straight line is a slope of 64 over Reynolds number. And we're going to show how that come about. That's your in-class problem. Right? Does that ring a bell? Have you seen this? Why do I have to tell you there's a cast iron pipe as opposed to polished aluminum pipe or glass pipe? How would that change something? Huh? Roughness. Yeah, roughness factor. Okay, cast iron is cheap, but it's not very smooth. So a function also that would dictate the so-called friction factor is the relative roughness, E, which is for this problem. Once I told you what pipe it is, you can look it up from the manufacturer on those pipes, they will tell you that. For this reason of using the Woody diagram. So cast iron pipe, the roughness is approximately 0.25 millimeter, and it changes as the pipe gets old. Why? Yeah?
So, actually, have a question. So,
Sure.
in the textbook, it said that the bound should be 2,100 instead of 2,200 for lambda.
Yes?
Is that 2,100?
No, 1,000. Did I say 100?
Is it 2,100 or 2,300?
For the Reynolds number, the range of which, well, first for our homework assignment, we picked arbitrarily the value of 2,300. That is academic. But the actual range of which the Reynolds number can change from laminar to turbulent is something like 1,000 to 4,000. Not 100. I say 100. I misspoke. Oh, 21. I'm sorry. Yeah, that's fine. Yeah. 2,100 is that.
Yeah.
That's fine, but I want you to remember this is just purely academic. This is just so that I can grade you. But really, I mean, when you go to the real world, what I want you to remember is not that 2,100 or 2,300. I want you to remember it's a range. Okay? But good clarification. So, anything else? Any other questions? So, you've seen this. So, today, another 10 minutes or so, we're going to show you how this comes about. Okay, so first and foremost, did you get this graph from dimensional analysis in chapter 7? Can you tell me what CP will change with Reynolds number purely based on dimensional analysis? Can you? You can? Well, let's review what we did with dimensional analysis. So I'm going to go after this Woody diagram. So what I have is flow in a pipe horizontal for the time being so that I can develop this Woody diagram. And my objective when I'm done is quantify how change in pressure as a result of friction. So back in chapter 7, we went through this analysis. What is the subscript L fish represent? If you draw the velocity in the pipe accounting for real frictional effect, what would that profile look like? It's gonna be a parabola or something that is not uniform. That's too complicated for us to deal with, so we're gonna just assume with that given profile, I can obtain an average velocity, which is what you have done in chapter 3 when we deal with continuity. We look at how one can average this profile to get an average velocity. So dimensional analysis, all we have done in chapter 7 is this. Can you tell me what that function is like? Solely on the basis of dimensional analysis? Can you tell me that the pressure will decrease as a function of Reynolds number? No. It doesn't tell me the shape of the Moody diagram by any means. This is all I can tell you at the end of dimensional analysis. To obtain this function, Mr. Moody had to do a lot of experiments. And your homework is kind of related to how the experiment can be done, so that I can somehow, some way, change this to a friction factor. And this now becomes the famous Moody diagram. The question is, how do I make that link? And that is through the energy equation. Right? So I'm going to take my horizontal pipe and apply energy equation to that analysis. How can I simplify this equation for a horizontal pipe between point 1 and point 2 very quickly? No pump, nothing in between. Can you touch the pressure? No, that's what I'm after. Can you tell me something about the velocity? What? What can you tell me? Huh? You hesitated? I wonder why you hesitated. What is confusing you? Tell me, what is confusing you? Do you believe in continuity? What does continuity tell you? You are still not sure. Something is bothering you. I think I know what that is, but I don't want you to tell. I want you to tell me. Why are you so hesitating now? All of a sudden, this is no different than what we did with invisible flow and the use of continuity. What can you tell me about V1 and V2? You're still not sure. What have to happen? What have to happen if this is a steady state, steady flow problem? Rho VA to rho VA. So what's the conclusion? What's the difference in velocity? What's the difference in density? None. What's the difference in area? None. What can you tell me about velocity? Why are you hesitating? Well, because viscosity is confusing you now. You may say, well, there are not enough pressure to push the flow from 1 to 2. Then the velocity of the flow may stop in the pipe. And that will happen if your pump power is not enough. But is that a steady problem? No, it's not, because what's coming in is not going out. That's a transient problem. That's where the engineer turned on the pump, the flow started, halfway to stop. Because the poor guy or girl make an estimate and forget the factor of 30 and buy the wrong pump. And there's not enough power. But that's not a steady problem. So don't let friction confuse you. If it's steady, as all problem for us is steady, what comes in must go out. I don't care how much friction occurs. Do you get it? This is very important and can haunt you if you're not careful. What else can I neglect? no change in elevation, horizontal pipe. Any shaft work in this inlet and outlet, or this just section of pipe? No, there's no pump or turbine. So that turns out allow me to express my head loss due to friction purely as a pressure drop, and it's nothing but OGH. So that's 7 liters of water. It just translates to how many kilopascal of pressure drop due to friction, OGH. And my pump better provide enough pressure-wise to overcome that delta P in terms of kilopascal, or the flow is not going to go. All right? So dimensional analysis, which is halfway here. Now I'm going to replace this delta P with the delta P in here. So I call it equation 2, equation 1. I better watch my time. It's just algebra. So combining my dimensional analysis with the use of simplified energy equation for horizontal pipe, I have now this equation, and this is where Mr. Moody comes in. Experimentally, he showed that, and it's kind of intuitive, the amount of frictional head loss is directly proportional to the length. Longer the pipe, more losses, directly proportional. And inversely proportional diameter, the smaller the diameter, more frictional head loss. And from that observation, which sounds pretty simple, and with further algebraic manipulation, I can now factor out the dependency of L over D from my equation. Just take it out, because I know by experiment, again, not by dimensional analysis. This is after I've done a lot of testing in my laboratory, and it's kind of what you do in the homework. I've observed this is now my final form of the relationship, and this function of Reynolds number and roughness factor is what I will plot in this famous Moody diagram. And that's the result what we see on the far right. So the friction factor now originated from experimentation, which is a function of the Reynolds number and the relative roughness. And all that boils down to now my head loss. That 7 liters of water loss for my fire hose problem can now be estimated based on this final equation. The friction factor will be determined from the Moody diagram, and the rest are parameters that you have to tell me how long is the pipe, what diameter, etc. to get the pump to work. All right, so this is part of what the algebra is for your in-class problem, which is very straightforward. Now I'll stop right here and give you time to do the quiz. So it turns out for laminar flow, the pressure drop can be explicitly given by this equation through half a page or less of algebra, 3 or 5 lines. Show me that for this given pressure drop for laminar flow, that when you work through the algebra using the equation I posted, the friction factor is 1/4 the Reynolds number. Right, this is the 5 minutes homework, not 5 hours. Whenever you're ready, you can start your quiz.